Hello everyone, welcome to topic 9.9, cell potential under non-standard conditions. By the end of this, you should be able to explain the relationship between deviations from standard cell conditions and changes in cell potential. So previously we looked at cell potentials which were only at standard conditions, 1 molar, 1 atmosphere, 298 Kelvin. In the real world, though, it is rare that the conditions perfectly match standard conditions. So we will see the cell potentials differ from what our predictions are. That's normal. Reality sucks compared to a perfect world. So there we go. The cell potential will vary with a change to the concentration of the solutions in the system. The cell potential, or voltage, is the force that drives the reaction to reach equilibrium. When the reaction is further from equilibrium, the driving force is greater, and thus the magnitude of the cell potential is greater. Electrochemical cells are not at equilibrium, right? There's a force driving them towards equilibrium. Since the reactions are not at equilibrium, we cannot use Le Chatelier's principle to predict how a reaction will react when the pressure, concentration, or temperature changes. Since we know that the standard cell potential is calculated at 1 molar, 1 atmosphere, we know that the value for Q, or the reaction quotient, would have to be 1, because everything's 1. And so remember that Q is the concentration or the pressure of all of them raised to their exponent. And so that can also be the pressure raised to the exponent, right? Oops, that's a denominator. Ooh! Oh no! There, we're back. Sorry, guys. Raised to an exponent. Okay, and since if everything's all 1, it's 1 over 1, because any 1 to any power is still going to be 1. So Q is going to be 1. Okay, as the cell reaches equilibrium, the magnitude of the cell potential decreases to 0. So E gets closer to 0. A value for cell potential of 0 means that the reaction is at equilibrium. The Nernst equation, which is this bad boy, shows the relationship between the cell potentials at non-standard states, so this is non-standard, and the standard state, which is this one. That's what this little 0 sign means. This is standard, and then non-standard is this guy. Okay, and notice how Q is going to help with that. Okay, and in this case, the R for this one is the 8.314 joules per mole Kelvin, because we're talking about cell potentials, which utilizes energy. The rest of those we've covered recently. You should be able to explain qualitatively how non-standard reaction conditions will affect the voltage of a cell. I do not think that you will be asked to do the calculations for this. This is important for changes to the concentration, as you should understand how changing the Q will change the voltage of the cell. And that's going to be in some of the practice problems, so we'll get there, guys. When the conditions deviate from standard conditions, so Q is less than 1 in a direction that takes it further from equilibrium than the Q equals 1, the magnitude of the cell potential is greater than the standard. And so we can show that here. Consider a cell with a reduction reaction of zinc and the oxidation reaction of calcium, and we have a balanced overall equation shown here. Boom. So this is our electrochemical cell, and it's a voltaic cell because it's positive. The value for K, if we plug it into this equation, is going, and then we're going to rearrange a little bit. So we end up finding G, and then we can plug G in here, and we find K, which is super freaking huge. Look at that, 71st power. So that's very, very product favored, right? The K expression is given for this. So you should see at equilibrium a lot of this and almost none of that. With standard conditions, the Q value should be 1, no matter what they are. If we change the concentration of zinc to 2 molar, the Q value decreases to 0.5, right? The Q value is further away from the KEQ than 1 is. Therefore, the cell potential increases. So you should have a greater E value. You can also put this into the Nernst equation as they demonstrate here. And then we can compare this to the original up here, right? And see that they're different. Yeah, it's not a lot, but it's kind of significant to change the cell potential. If you change the concentration of the calcium ions to instead, Q is then 2, not 2 molar, it's unitless, it's 2. This new Q value is closer to KEQ, so the cell potential will be less than the E value. We notice it does decrease, right? Our original standard one is the 2.11 volts, right? So decreasing Q makes E go up, increasing Q makes E go down. Okay. So a concentration cell is another type of electrochemical cell. It is similar to cells that we have seen in the last few lessons, but you have the same reaction in both half reaction beakers, though they have different concentrations. We can predict the direction of the electrons will flow by looking at which direction the thermodynamically favored reaction would need to go in order to reach equilibrium. So we have the reaction given here, and they're telling us like which ion we're talking about, the more concentrated or less concentrated. So the voltage will be calculated as follows, and we see that here where we substitute in all the stuff we know about this reaction. We know that the standard potential, if their concentrations were both 1, should be 0. So this is E cell, the E standard conditions, but it is 0 because that's assuming that they are both at 1. And then we plug in all the other constants we know. And then for Q, it's always products over reactants. So this one goes here, and this one goes here. And the solids are omitted because they are not part of an equilibrium process, like they aren't counted because they're considered infinitely large concentrations. So they don't count. And so you recalculate and you see that the potential for this one is 0.030 volts. Please note in a concentration cell, the E value is 0, as I shown here, because the reaction at the anode and the cathode are the same under standard conditions because they're both either going to be at 1 molar or they'll both be at 1 atmosphere, depending on if you're talking about in aqueous solutions or gases. Okay, so looking at this, here's how Gibbs free energy, the equilibrium constant, and cell potential are all related. And so I believe all of these equations are on your constant equation sheet under electrochemistry. So verify that they are there, but also know that they're useful in these sorts of problems, and they will pop up probably. So make sure we are used to seeing them and used to using them, and we are going to do that now. So let's do an I do. Consider the thermodynamically spontaneous cell at 298 Kelvin composed of 100 milliliters of 1 molar iron ion in 1 beaker with an iron electrode and 100 milliliters of a 1 molar manganese ion with a manganese electrode. The beakers are connected with a porous disc, so it allows the ions to flow and thus connect the circuit. And they are connected with a wire connected to a voltmeter. And so then it gives us the expression. Qualitatively describe the effect on the value of Q and the voltage when the following changes occur. We have 1.1 moles of iron nitrate added to the iron beaker. Well, that means that this is going to increase. So our reactants increase. So for Q, right, it is then, so I'm going to start from the beginning. So iron ion concentration increases. Right, so this is going to cause, since iron is a reactant, Q will decrease because the iron 2 plus ion is in the denominator, and we know that a decrease in Q is going to cause the cell potential, not standard cell potential, the cell potential to increase. Okay. If we add 100 milliliters of distilled water to the iron beaker, well, adding more plain water with no iron in that is going to cause the iron concentration to decrease. It actually is halved. So that causes Q to increase, which then will cause E to decrease. Next, 100 milliliters of distilled water is added to both. Well, since we're adding it to both, the iron and manganese concentrations both decrease by the same ratio. No change happens to, so because it's the same ratio, right, that ratio technically cancels out in the Q component. So no change to Q, which results in no change to R. No, not R, E. Sorry, I don't know why I said R. Okay, so now we're going to look at our redo, and this is a half cell. We're going to look at what this is. So first, we're going to calculate the cell potential when the right beaker is filled with zinc at 2 molar. So we're going to use the Nernst equation. So E equals E standard minus RT over NF ln of the concentration. So zinc 2 plus 1 molar over zinc 2 plus 2 molar. Okay, so we're going to plug in with what we know. We know that this is going to be 0 because standard conditions when it's a concentration cell, right? They're both the same liquid. Standard conditions, they're both 1 molar, same thing at 1 molar, same concentration. No, it's going to be at equilibrium, right? There's nothing different between the two, so nothing's going to happen. So E is 0 volts minus R is 8.314 joules per mole Kelvin times 298 Kelvin over N, the number of electrons, which it gives us here is 2 moles of electrons. And then F is 96,485 coulombs per mole of electrons. And we're going to multiply that by the natural log of 1 molar over 2 molar. Okay, and then plug all this in, and we end up with, and I'm kind of running out of room, so I'll write it here. E is equal to, because this goes away, then we do all this math here, then we multiply it by the natural log of 0.5, because 1/2 is 0.5, 0.0089 joules per coulomb, which is the same as 0.0089 volts. So that is our cell potential for this one. Now we're going to identify the cathode and the anode, okay, when the right beaker. So this is our 2 molar zinc, and this is our 1 molar zinc. Okay. So the anode is going to be the one that gives up electrons. So I want to make more ions so that these two concentrations are the same. So my zinc is going to go from Zn solid to... So we know that since the concentrations aren't the same, the solid is going to make the ion and send electrons up through the wire. That means that this is going to take electrons and make zinc solid over here. Okay, so since the solid is losing electrons on this side, so it's being oxidized because a loss of electrons is oxidation, this is my anode. So then that means that this is my cathode. Okay. And then we're going to draw an arrow to indicate where the electrons go. Well, since this is becoming an ion, my electrons are going to shoot up this way through my voltmeter and generate that positive 0.0089 volts, and then into this electrode so that it can be accepted by the ions here and form that solid over here. Okay. Okay, so that concludes the 9.9, 9.8, 9.9 notes. Please complete the UDOs, check your work, and thank you for tuning in.